is the solution set for quizzes 4 through 6. Posting at midnight tonight to help you with your studying over the weekend in preparation for exam 2. They will go in order, so we'll start with quiz 4. First slide always takes a second for whatever reason. There we go. So question 1 on quiz 4 says a skier slides down the face of a mountain, rising at an inclination of 30 degrees above the horizontal. Which of the following forces may act on the skier? So to deal with these Newton's laws type problems, just like with kinematics, the first thing that's usually useful is to simply draw a picture of the situation. So we have a hill that's described as being a slope, 30 degrees. The hill makes a surface. For the sake of identifying types of forces, we need to know the types of contacts. So this is a surface contact with a skier that I've simply represented as a block. Okay, I put the two in contact. I have the direction of motion of skier highlighted. I put a circle around the object. I look to see what that circle intersects with. It intersects with the hill, the surface. So I know that in terms of contact forces, I'm limited to only contact forces that come from contact with a surface. And I know that I'm existing near the surface of Earth, so that I should have a weight force. So I've identified where the forces can come from. I can start with weight, draw a free body diagram. The dot represents the object. The rule for weight is it exists, it's proportional to mass, and it points down. So we have a weight force. Surfaces can present up to 2 named forces. We have a normal force, which would point perpendicular to the orientation of the plane of the surface. And then parallel or along the plane of the surface can exist a frictional force. In this case, that friction would be a kinetic friction because we are sliding. Those are all the forces I can identify. We look to our answer choices: weight force, yes; normal force, yes; kinetic friction, yes. All of the above would be my answer. Both weight and normal, but not friction, that's not accurate. Okay, 2. In the previous problem, which force acting on the skier will have the greatest magnitude? So we've already drawn the free body diagram for the previous situation. What we know is we have a weight that points down, a friction that has to point along the surface, and a normal force that points perpendicular to the surface. If we look at this, if we label perpendicular surface as the y-axis and along the surface as the x-axis, then the normal force and the weight force are the only 2 forces that have y components. And independent of whether or not the skier is accelerating, we do not expect them to be accelerating perpendicular to the surface of the hill. Meaning y should be 0 such that F net y should be 0 such that the normal force must be equal to the y component of the weight force. That's the weight force projected onto the y-axis. What does that mean? That means weight is going to be larger than normal force. Normally, the coefficient of friction is less than 1, such that normally we would assume that normal force is greater than a frictional force. On a test, I would have to go a step further to make this unequivocally clear, like by providing something about the kinematics. Like, for example, I could have mentioned that the skier was sliding down the slope at a constant velocity or accelerating down the slope, in which case you could explicitly relate the size of the kinetic friction to the size of the x component of weight and compared to the normal force that way. Or I could have given you the coefficient of friction, for example. But under normal circumstances, frictional force will be less than normal. You had multiple attempts to get at what I was thinking for the problem in this case, in which case weight would be greater than normal force would be greater than friction. This one didn't actually ask us to rate them all, it just asked us to rank greatest. Weight would be greatest. All right. We had in some of our in-person meetings, I think this example of your sister's on a skateboard, you're standing on the ground, you push your sister. She accelerates along the floor, you don't. The question is then, how does the magnitude of the force you exert on your sister compare to that exerted on you by your sister? And this is a simple question just to reinforce Newton's third law. Despite the fact that the objects experience different accelerations and different net forces, these specifically called out set of paired forces are an action-reaction pair, meaning they must be equal to each other applied to opposite objects in opposite directions. So if we draw the free body diagram for both you and your sister, we can see why one of you could accelerate and one could not. This would be your weight. You have a normal force if you're on a flat level floor. There's some static friction between you and the floor. How do I know it's static? Because you don't slide along the floor. And there's some force applied to you by your sister, right? And so in this case, F net is 0 because all of the forces of y components, normal and weight, are equal to each other in opposite directions, such that when I do a vector sum, weight and normal force will cancel and sum to 0. And all of the forces with x components are also in opposite directions in equal magnitude. So static friction is simply canceling the push on you by your sister. Okay, now to your sister. Well, we said Newton's third law says if your sister pushes on you, you must push on your sister, and the size of those two things must be equal. That's what this question is trying to reinforce. So that just has to be true if we trust the model. Weight down, normal up. If your sister's sliding along the floor, we expect those two things to most likely be equal. Your sister's on a floor, there'd be a friction. She's on a skateboard, we'd expect it to be a rolling friction. And that rolling friction would happen to be smaller than the push you provide to your sister. How do I know that? Your sister accelerates in the direction of your push, so she must have an F net in that direction. And so the reason your sister accelerates and you do not, despite the fact that you push on each other with the same force, could have to do with a lot of things, like you might have different weights and therefore different normal forces. But at minimum, it's because the force of static friction, somehow, some way, on you is greater than the force of rolling friction experienced by your sister. And notice that that is not the action-reaction pair of forces between you and your sister that must be equal. All right, we brought back the frog from a previous quiz, had him or her jump straight up from ground level, reaching some height of 1 meter. And we're told to do this, the frog pushed downwards on the ground with a continuously fixed magnitude force. So that's important that the force was constant. We're told the amount of time the force was applied for. The question then is how large was the force exerted onto the ground by the frog when pushing downward to jump in this situation? So during that 0.15 seconds when the frog pushed downwards to jump upwards, how big was that force? Well, to get the size of a force, we need to analyze the kinematics of the situation. And what we really realistically are after is what was the acceleration of the frog during that short period of time when it remained in contact in the ground, meaning when it was pushing on the ground and therefore the ground was pushing up, what was its acceleration during that brief time window? If we know the acceleration during that brief time window, we will know the net force during that time window. And if we know the net force during that time window, we can draw a free body diagram, look at all of the forces, and determine potentially the size of all the individual forces. One of those forces will be between the ground and the frog. We can use Newton's third law to say if the ground pushes the frog up, that must equal to the force that the frog pushed the ground down with. So let's go through this. Step one, I need to figure out the acceleration of the frog. I don't have it directly, but I have enough information about the resulting motion of the frog after it leaves the ground to determine what its initial velocity must have been when it left the ground. And how would I do that? I'd go back to the kinematics chapters we just did for exam 1, and I'd say I have a kinematics equation that says v final squared is equal to v initial squared plus twice a constant acceleration multiplied by a vertical displacement in this case. If I rearrange that, I can solve for the initial velocity. This is the period of time while the frog was airborne, not in contact with the ground. And what I can do is I can pick out the time it took to reach its maximum height, which rather the distance to its maximum height, which we were told was conveniently 1 meter, right? They told us it goes 1 meter up. That must be its maximum height. I know something happens there. What I know is that the velocity when I reached that position must have been 0, the vertical component of velocity at minimum. If it went straight up, then total velocity, right? So if I look at this, during free fall, I have an acceleration of 9.8 meters per second squared. Um, and I have a 1 meter displacement, and I multiply that by 2, right? I've dropped a negative sign, I think, through algebra here, is how this works out being a positive number. Subtract 0 is 0, and I'm going to get the square root of all that is 4.427 meters per second. All right, so now I know the velocity the frog left the ground with. I know before it jumped, it had a velocity of 0. So I can use this then to determine the acceleration of the frog during the period of time that it was pushing down on the ground. The change in velocity during that time would have been 4.427 meters per second from 0 to that. It did that in 0.15 seconds, and we were told it was a continuously fixed force, so we can assume there's a continuously fixed net force. We can come back to that if we need to, which means there is a continuously fixed acceleration. So this equation is fair, in which case I would find that my acceleration is 29.51 meters per second squared during the period of time that the frog is pushing downward on the ground and beginning to accelerate itself upward. All right, so now I used Newton's second and in parentheses and third law to figure out the thing I want. Now that I have the acceleration, I know that Newton's second law tells me F net always equals ma, so then it's just a question of what actually makes up F net in this situation. To figure out what makes up F net in any situation, I draw myself a free body diagram representative of the situation. I have a frog, it's on level ground. The frog is near Earth, so it has weight, weight points down. The only other force that could act on the frog would be a normal force. I know that the frog accelerates up such that F net must be up. So the normal force must be greater than weight because on this vertical axis, I have no other forms of contact to give me any other forms of forces that could point in this direction. So this must be the only two forces that I have to consider here. So normal force has to be greater than weight, and normal force minus weight would therefore be equal to the mass of the frog times the frog's acceleration. And that's what we say here. F net is equal to N minus W from the free body diagram and our knowledge of the situation. I've chosen up to be positive, therefore, because acceleration is up. That's then equal to F push minus mg. Where did this F push come from? Because if the normal force is the ground pushing on us, that must in turn be equal to the force of us pushing on the ground by Newton's third law. So this is the thing I want. Ultimately, that minus the weight of the frog, which is the mass of the frog times g, will be equal to the mass of the frog times a, where a is then this during that period of time. Okay, so now we can go ahead, rearrange. It looks like what we did is we pulled the mg across the equal sign to solve for F push, such that F push is then equal to mg plus ma, which then is just equal to m times g plus a. I know g, I know a, multiply by m, and I'll get that the force of the push must have been 39.31 meters per second squared multiplied by the mass of the frog. I know that the weight of the frog is m times g, which is 9.8. So if I was to compare the force of the push to the force due to weight, which is what all of my answers seem to be doing, then I can just say, okay, this thing divided by that thing would be equal to what they're equal to divided by each other. And when I do that, we notice I can get rid of the mass of the frog, and I get two numbers compared to each other, which 39.31 divided by 9.8 is just 4.01. If I then multiply both sides by W, I'd get that the force of the push is about equal to 4 times the weight of the frog. That's the top answer choice. All right, we use a pulley to pull a piano straight upward with vertically attached ropes at a constant velocity. Which of the following must be true? I didn't say how many ropes, but I said it was just ropes. Ropes have tension. And the key here is constant velocity. Constant velocity is one of the buzzwords we're always looking for in these set of chapters because we're always looking for the kinematics and specifically the acceleration of objects. Constant velocity means zero acceleration. Zero acceleration means zero net force. So now I just look at the situation. I see ropes, vertical, up. Object has weight down. I don't see any other contacts with the piano. Therefore, I only have two forces. One points up, one points down. Since F net must be zero, those two forces must be equal to each other. Now, could I have multiple ropes? Sure. This tension is just representing the total tension across all of the ropes that point up. That total must equal the weight of the piano. And that's what this second answer choice says. The total upward force of tension, that's this one, must equal the weight of the piano during this time. And Newton's second law is Y. All right, chapter 5. This is kind of more than more problem solving with Newton's laws. We have a car parked on a hill as shown. The angle of inclination of the hill is 15 degrees as shown here, which the following free body diagrams accurately depicts all of the forces in this situation. Keyword here, parked. Normally when we think of parked, we think of not moving. When we think of not moving, we think of not accelerating. Not accelerating by Newton's second law means zero net force. All right, we look at contact, draw a circle around the car. What do we see? We see that the circle intersects a surface. So a surface is touching the car. A surface can contribute two contact forces, one being a normal force, where normal forces are constrained to point perpendicular to surfaces. Here my surface is at an incline, so my normal force should be at a perpendicular incline. And frictional forces, which are constrained to point along the surface, which could be anything along this line. Based on the answer choices you had, I believe only one gets the job done in terms of having the right forces, pointing the right ways, and balancing out to have a net force of zero, and that answer choice is this one. Why does that work? Well, normal force is perpendicular to the incline of the hill. Static friction points along the hill, up the hill. Weight points down. So far, so good. They all follow general directional rules based on contacts and long range rules. If I then look and were to compare kind of sizes, I have a y component of normal force and a y component of friction. They both point up. By eyeball, it looks like if I were to sum those up, they would be equal in magnitude to the magnitude of weight force pointing down, such that F net y would be zero. And then if I look at the forces with x components, it's only normal and static friction. Normal force goes to the left about that much. Frictional force seems to go to the right about the same amount. Those would similarly cancel to zero when I did a vector sum of F net x, such that F net total is zero, which again, the word part tells me should be the case. Question 2. Assume the same scenario described in the previous problem. So same scenario, had the car on a 15-degree incline, it's parked. What happens if the brakes in the car fail such that the wheels become free to roll? Well, now we're not going to assume F net is zero anymore. Assume that contact between the wheels and the pavement creates a certain coefficient of rolling friction. At what rate will the car accelerate along the inclined surface? So now we're assuming the car is rolling down the hill and we want to know what its acceleration will be. So if we're looking for an acceleration, we're assuming F net is not zero, and we're assuming that F net will point down the hill. So F net x should point that way because acceleration should point that way. All right. Well, the x component is where our acceleration lives, so it makes sense that we might start with that. We've drawn, and this is a skill I showed you in some videos, but anytime you have inclined planes, it's useful to draw two sets of axes because usually the angle is between a conventional vertical horizontal paradigm in comparison to the plane of inclination. That's very common for how inclinations are described. So it's useful to have both sets. I have a horizontal and a vertical, and then I have the plane of the inclined hill and perpendicular to the plane of the inclined hill. And I know that I like to work with one of my components being in the direction of the acceleration, which leaves the other component to be perpendicular to the direction of the acceleration in these problems. In that case, I want my x-axis to be along the hill. That's the way we'll accelerate. My y-axis will then be perpendicular to the hill. And then the nearest neighbor axes from the other set of axes, meaning horizontal, vertical, I'll just give primes. They're my reference axes. Why? Because the hill is described as being an angle between horizontal and the plane of the surface. So that's my angle there. It lives between x and x prime. And I can use that to do the trick we've talked about before. Angle, not angle, angle, not angle, angle, not angle, angle, not angle. So I get 4 repeats of the angle, and I know everywhere in this diagram where the angle lives. That's useful because I know in these situations I'll always end up with at least one force because weight won't point at an incline, it points straight down, for which I'll need to find components if I want to work in terms of x and y components of net force. So again, car rolls down the hill, that's our x-axis. So it makes sense that we'd want to start solving this by thinking about what happens in terms of the x component of the net force. If I look at my diagram, same one from the previous problem, I'll have a frictional force which tends to resist my motion. Well, the car is going to roll down the hill, so the frictional force must point back up the hill. I have a weight force that points down and a normal force that points perpendicular to the hill. These forces are not necessarily drawn to scale, but they are drawn in the correct directions with the correct labels. So now if I look at this, I ask myself, okay, how many of these forces have x components, not x prime components, x components? Well, the normal force points along the y-axis. It does not have any x components. So normal force does not have an x component. The frictional force points up along the x-axis, up and right. That has an x component. It points along the x-axis to this way. What other force has an x component? Well, weight doesn't point along either axis. It's in between the two. This is the x-axis, this is the y-axis, weight's in between them. That means weight will have a y component and an x component. So weight definitely has an x component. Which one of these two things, that there's only two forces now that have x components, must be bigger? Well, I know I accelerate in the direction of weight's x component. So weight's x component must be bigger than rolling friction in this case. So I'll set it up such that the positive direction is down and to the left along the x-axis. In that case, the x component of weight minus the rolling friction, that's my net force, must equal my mass times my acceleration in that direction, in which case my acceleration is positive, down and to the left. All right, so then I can just expand upon what these things would be. Weight, by definition, is mass times the gravitational acceleration constant. And the x component, well, this angle lives here. My x component would be down here. My x component is opposite the angle, so it must be weight times the sine of theta is the x component of theta. So mg sine theta, that's just wx. Rolling friction can be defined in terms of normal force. So I can express the rolling friction in terms of the coefficient of rolling friction, which I was given, multiplied by the size of the normal force, which I do not currently know. But whatever that is, it would be equal to the mass of the car times the car's acceleration in that direction. All right, well, what I see now is I have an equation that relates to mass, a constant, a known value, a known value, a normal force, mass, and the thing I'm looking for. Well, I know in my y-axis, I'm also going to have something that depends on mass, because I'm going to have a y component of weight. And I also see the other thing, the normal force that I can now get to show up in my x component because it relates to friction, is a y component force. So I can see a way to substitute to consolidate variables because I seem to have too many unknowns at this point. So if I now go to the y component of the net force, I can say how many of forces have y components? Well, normal points along the y-axis, so yes. Rolling friction points along the x-axis, so no. Weight points in between, so yes. The y component of weight would be here. And given the way the car is described to move, it will roll along the pavement, meaning it will not be accelerating perpendicular to the pavement. That tells me that F net y must be 0. That's why we set this up this way. And since I only have two forces with y components, they're just going to have to be equal to each other, meaning n minus the y component of weight must be 0. That means n is equal to the y component of weight, where here we're simply expressing the y component of weight in terms of what it would be equal to. Weight, by definition, is mass times acceleration constant due to gravity. And the y component of weight lives here, and here is adjacent to where our angle lives, so that would be cosine function. So mg cosine theta in this case is the y component of weight. So now what I see is I have something where n can be described in terms of mass, a constant, and trig function of something I know. And n was one of the things I didn't know in the equation that would give me the acceleration I want, meaning if I substituted this in for n, I would then have an equation where I'd have mass in the first term, mass in the second term, and mass in the third term across the equal sign, meaning mass is in every term on both sides of the equal sign. I can simply group and cancel out mass. Good reason to do this because now I've eliminated both the normal force and mass through the substitution. Those were the two things I didn't know. If I eliminate those two things, G I know, sine of theta I know, coefficient of rolling friction I know, G I know, cosine of theta I know, and acceleration is what I want. So this is clearly a path forward that will get me what I want based on what I have. So if I do that substitution, take this mg cosine theta, put it where normal force goes, I would end up with mg sine theta. This is coming from the F net x equation. So there's mg sine theta minus, we'd then get mu r times n, where n is mg cosine theta based on the F net y equation, substituted into the x component. There you go. And that is just equal to max. So we use the y component to find a definition for a normal force that we could substitute into the x component equation so that we could then solve for the acceleration we want. That's what we've done here. When we do that, mass cancels across the board, and I can solve for the acceleration. The acceleration is then just going to be equal to, well, I see both these things will have a g, so I pull the g out, and I'll have sine theta minus coefficient of rolling friction times cosine theta. And I know g, I know theta, I know coefficient of rolling friction, I know theta. Run that math, I'll get 2.25 meters per second squared, and I see that I knew my rolling friction to 1 sig fig, so my answer would be 2. And I usually put enough variance that if you keep extra decimals that you shouldn't, for sig fig purposes, you still get it correct. Question 3. So we have a pulley configuration, and we're told the tabletop is frictionless here. And we're told, oh, sorry, we're told that let me back up. That's why you got to read the problem first. I'm thinking of old problems. That's not what we're told. Start over. We have a tabletop. We have two masses connected by a rope, and what we're told is the pulley configuration, so the rope and pulley, is frictionless and massless. So we don't have to consider mass of the rope, we don't have to consider friction at the pulley, and we don't have to consider mass of the pulley. Then what is the smallest possible static coefficient of friction between box 2M and the tabletop? So definitely not frictionless because we're solving for a coefficient of friction. Well, most likely not frictionless at least. For which the boxes will remain motionless. Note the labels indicate that the mass of box 2M is twice the box of M, in case that was not clear. So this thing has twice the mass of that thing. They're connected by a rope. This sits on a table. And what is the minimum coefficient of static friction that this will remain in static equilibrium is what this question is effectively asking. So we can do this by considering both objects, box little m, box 2M. Start with box little m, it's hanging by a rope. If this whole thing remains motionless, then F net applied to box little m would have to be 0. If I look at this, I would have a tension force pointing up due to the contact with the rope, and a weight force that points down due to presumably being on Earth. So tension would therefore have to be equal to the mass of the little box times g. That would have to be true if this remained in static equilibrium. All right, then I can go to the other end of the rope, and I look at that, draw a circle around it. I see it touches a rope and it touches a surface. So I could have as many as 3 contact forces: friction, normal, tension. And of course, I'll have to have a weight force. If I was to draw the free body diagram for this, weight would point down, normal would point up, tension would point right because the rope is pointed right. And friction would have to point left because the surface is horizontal. And if this box were to accelerate, it would accelerate right. So if it doesn't, friction would have to point left. Okay. Got the full summary for box 2M. In that case, if I deal with just the horizontal component forces, because if it does accelerate, that's the direction it would accelerate, then if it remains in static equilibrium, then the tension on the rope that points right must be equal to the static friction that points left. But we know static friction has a limit. So the static friction has to be less than or equal to the greatest possible static friction, Fs max. And that has a relationship with normal force, where the coefficient of static friction times normal force is equal to your maximum possible static friction. So in this case, if we're looking for the smallest possible, we're effectively setting these two things equal to each other such that T is being set equal to mu s n. And n, in this case, is going to be equal to the weight of the box because there's only two forces with vertical components. Normal force would be up because the plane is horizontal and perpendicular to horizontal is up, and weight points down. So in that case, the normal force would just be equal to the weight of the box, which is in this case 2m is the mass of the box times g. So what we're saying here is T equals mu s times 2mg. And what we're then going to relate is that the tension applied to this mass and the tension applied to this mass are a third law pair. It's the same rope transmitting the tension to two opposite ends. They're interacting objects. So what I can do is take this equation, and I have T, I have this equation and T, and say, well, then this thing and this thing would have to be equal to each other at this limiting condition. So T is equal to mg, that's one definition of this tension. And at this limiting condition, T would also be, we could say less than or equal to, but if we set right to the limit, equal to 2 times mu s times mg. And what we see is we get mg, so then we'd have 1 less than or equal to 2 mu s. 1 over 2 must be equal to mu s by algebra. So half would be the answer to this question. Question 4. Car is pushing a truck steadily backwards at 10 meters per second. So steady 10 meters per second. That means velocity is fixed. That means acceleration is 0. That means net force is 0. But we're rolling this way, so we would have a rolling friction in both cases. Assume that both vehicles' tires have a rolling coefficient of friction of that much. Okay. Consider the following forces acting upon the different objects. You've got the force of the car's tires pushing backwards on the pavement. So tires are going like this and trying to push backwards against the pavement. The force of the car pushing on the truck. So the car is pushing the truck that way. And the force of the truck pushing on the car. Well, that's a Newton's third law deal. If the car pushes the truck must push the car. And then finally, the rolling friction exerted on the truck by the pavement. The truck's rolling this way, so there'd be a rolling friction to slow it down, point it back. Which of the following choices correctly ranks these forces from greatest to smallest in magnitude? So what we'll do is we'll draw two free body diagrams. We'll only consider the x components, meaning the horizontal component forces. Both objects are on a surface. Both objects are touching each other. And that's pretty much it. So the surface can exert frictional forces. In this case, actually, technically, the force of the pavement on the car is a type of frictional force. It's actually a static friction. So when you roll, you actually have a static friction is what propels you forward. That's where the car rotates without slipping. So the car attempts to push the pavement backwards, the pavement pushes you forwards. That's a third law pair, like static friction. But then you also have this rolling friction that actually slows you down over time. So pavement on car, that must be what gets the car to go forward. It must be equal to the force of the car on the pavement, Newton's third law. Rolling friction back, force of the truck pushing on the car. That would be what's acting on the car horizontally. If we were to then look at the truck, well, if the truck is pushing back on the car, then the car must be pushing the truck forward. So the car pushing the truck forward is the obvious one. This is kind of the response pair. The truck must push back. These two have to be equal to each other because that's an action-reaction pair of forces. It's the same two objects exerting one force on the other and back. Okay. And then finally, the truck would also have a rolling friction. Based on the kinematics, we know that the acceleration for both objects is 0. So if we start with the truck's being pushed by the car. It has a rolling friction. Those are the only two forces that have horizontal components for the truck. Therefore, these two things must be equal for the truck. So force of car on truck must equal rolling friction of truck. What does that mean? That means both of these things must also be equal to the force that the truck pushes back on the car. However, the force of the pavement pushing the car forward has to be greater than the force of the truck on the car because there will be some rolling friction exerted on the car, such that the sum of these two forces is equal to this one force. So this must be bigger than either one of those. So finally, this must be equal in magnitude to the force that the car was pushing backwards on the pavement, because again, that's a third law pair. Putting it all together, the biggest one should be between the pavement and the car, so FC on P had better be bigger than everyone. There's three choices that do that. Um, and then I look at those choices. All of the other ones are then between the car and the truck and the car, and the rolling friction of the truck. All of those are equal. This equals that equals that. And that's this answer choice. Question 5. Assume the same conditions as those described in problem 4. If the mass of the car is 1,000 kilograms and the mass of the truck is 1,500 kilograms, then how large is the size of the force exerted backwards along the pavement by the car's tires? Okay, and we're going to answer in Newton. So now we're going to complete the full free body diagrams. They look similar to the previous problem, except that now we have the vertical component forces also. In both cases, we have a weight of the object and a normal force from the pavement supporting the weight of the object. All right, so if we put this whole thing together, we know that the force that we're looking for is the car's tires pushing backwards on the pavement has to equal the force of the pavement pushing the car forward, this force. That, in turn, because we know these things are not accelerating, has to be equal to the combination of the rolling friction applied to the car and the force of the truck pushing backwards on the car. So this summed must equal that because F net x has to be 0. Okay, well, now we're going to play another third law game, and that's to say this thing here has to equal that thing there. So we can expand Ft on C must be equal to Fc on T, and we can expand the definition of rolling friction on a car to relate it in terms of the normal force applied to the car through the coefficient of rolling friction. All right, so we turn this into this by third law, and we simply expanded this to define it in terms of normal force. In this case, we know that normal force is just equal to weight, so we can expand this to express the normal force acting on the car in terms of the weight of the car, because those are the only two forces with y components, and F net y is 0. We were here, we got here, and then so the force of the car on the truck by the truck's free body diagram has to be equal to the rolling friction of the truck because those are the only two forces with x components and the truck is not accelerating. So car on truck becomes rolling friction of truck. Okay, continue. Define rolling friction of truck in terms of normal force applied to truck. So you get coefficient rolling friction times normal force applied to truck. Define weight in terms of mass times gravitational acceleration constant for the car. Play the same game to completion for the truck. And now we have an equation by which the force of the car pushing backwards on the pavement is expressed in terms of the coefficient of rolling friction applied to both tires, multiplied by the mass of both objects, multiplied by gravitational acceleration for both objects, must be equal. So we know the mass of the truck and the car. We know the coefficient of rolling friction between both objects' tires and the pavement. And we know the gravitational acceleration constant, meaning we can solve for the size of this force, which is to two significant figures, 2,500. And again, I believe I give enough variance in the acceptable answers that if you put 2,450, it would still be marked correct. All right. Quiz 6, circular motion. So the kinematics of circular motion and rotation, centripetal acceleration, centripetal forces, and then big G gravity and orbits. So starting with kinematics, an object's traveling along a circular trajectory with a constant speed of 10 meters per second. So we have a speed. How large is the centripetal acceleration of the object while it continues to complete one revolution along this trajectory every 3 seconds? That means the period is 3 seconds. All right, well, I know that an angular velocity is defined by the angle you sweep in one circle, which is 2 pi radians, divided by the time it takes to do that, which is called a period. So 2 pi radians per 3 seconds must be the angular velocity of this revolution or rotational motion. All right, I also know that speed is equal to angular velocity times radial distance. Well, I've now got angular velocity and I was given speed, so I can solve for the radial distance between my object and the center of the circle it's making. In this case, the radius would be the speed divided by the angular velocity, which is 10 meters per second, divided by 2 pi over 3 radians per second. And as we recall, when you do this, radians are a faux unit, meaning technically radians are unitless. You're just calling out the way you did a ratio to describe an angle when you refer to radians. And as such, seconds cancel, radians disappear. I'm left with meters, and I get 4.775 meters is the radial distance. Why did I do all that? Because if I was to first look at this problem, I'd say, how do you find a centripetal acceleration? Oh, there's an equation at the top of the quiz. It says centripetal acceleration is equal to circular speed squared over radius of the circle you make. And I would say, oh, I've got this thing in the problem, but I don't have this thing. That's what led to doing all of this, was a way to get that thing, right? So two-step process to get radius. First, if I get the angular velocity, and if I know the angular velocity and circular speed, then I can get radius. Get radius, I can get centripetal acceleration. It would then be 10 meters per second squared over the radial distance I solve for. I end up with 20.94 meters per second squared to two significant figures. Looks fair. My numbers of two significant figures would be 21 meters per second squared. Question 2, banked curve. Okay, so cars traveling at constant speed around a circular banked curve. Well, if I'm traveling in a circle, even though my speed is constant, when I have constant circular speed, I am accelerating. I'm accelerating because my direction's changing. The direction of my acceleration is towards the center of the circle I make. So in this case, I would be going around a circle. I would be turning to my left. My acceleration should point left. Okay, which of the following free body diagrams are then possible for the car in the described situation? Um, good. So in this case, I should have, let's see, I draw a circle around the car. I contact only a surface. Surface can give me two contact forces. One has to be perpendicular to the surface. That would be normal. And the other one can be parallel to the surface, either way as needed. If I'm not slipping, if I assume I'm not slipping at least, then it would be a static friction. So normal force, perpendicular surface, every diagram has that. Weight straight down, every diagram has that. And then it's just a question of the static frictional force. That's along the surface, that's along the surface the other way. Both of those things should be possible. And so, yeah, technically a constant speed could be zero. Let's start there. All right. Let me back up to talk about why all these, but car traveling constant speed around a circle, that constant speed could be zero, in which case you would have an F net of zero because you would not be accelerating in that one particular case. In that one particular case, F net X and F net Y would have to be zero. All of these forces point correct directions, and in which case Fsx equals Nx, and then the sum of Fsy and Ny would have to equal W. That seems reasonable. N, Y, W have to be, well, W plus FSY would have to be equal here. This is a car that is accelerating, but the acceleration would then be left because I have FSX and X, they point left. So I'd have F net X, that would be AX. That's possible. I could accelerate, meaning if I'm traveling with any speed, I will accelerate to the left. And finally, normal force. Do I need to have friction? Well, static friction only exists to the extent it needs to exist. So if everything's perfectly balanced such that the car would not be accelerating along the surface of the track, then I don't need the static friction, which is definitely possible. If the y component of normal force perfectly balances with the weight, I need that. F net y has to be zero because the car is not going to jump up or down off the track. then the y component of the normal force could be exactly however much I need to give me the centripetal acceleration I would have for whatever constant speed I have and the radius of the track. So all of these are possible. All right, question 3. Same thing as question 2. So if we go back, the angle is 25 degrees. There's our angle. And just like last time, when we have these inclinations, we're going to draw 2 sets of axes. But in this case, notice we change who's who. In this case, we make the x-axis the horizontal and the x prime the inclination. Why do we do that? Because the car is going to accelerate to its left. It doesn't accelerate down the incline of the track. It accelerates towards the center of the circle it's making. But nonetheless, we draw both axes so we can reference where the angle will live between each set, because we're going to have some that point along the prime set of axes and some that point along the non-prime set of axes. And the angles will live between those two. The question now is, what is the fastest speed at which the car can travel along the 100-meter radius? Now we have a radius of the curve without slipping. So without slipping, that means we would have to have static friction still. If the coefficient of static friction between the car's tires and the pavement is 0.85. Answer in meters per second. All right, this is a challenging problem. If we draw the free body diagram, we see that relative to the direction of acceleration, which we know will be to the left, which means we know we'll have a net force that points left, we're going to have 2 forces that have components in that direction. The static friction will have a leftward component, and the normal force will have a leftward component. Weight does not. It points straight down. Y components, I have 3 forces. Weight points down, so that definitely has a Y component. Static friction points down and left, so there's a down part to that. And normal friction points up and left, so there's an up part of that. All right. If I start with the Y component, I know that that has to be equal to 0 because the car will accelerate to the left, which means it will not be accelerating up or down. I've deliberately drawn it this way to pick out the direction it does accelerate. So since it doesn't accelerate up or down, then the Y component of the normal force, this guy, that would be in the up direction, must equal the sum of all the Y components of forces that point downward. That would be the Y component of static friction and weight. Why this way? Static friction could have also pointed the other way, but I have to think about what would give me the greatest acceleration. The greatest acceleration will be the greatest net force to the left. What will give me the greatest net force to the left? Well, static friction and normal force both point left. So we set it up this way. Y component of normal force minus Y component of static friction minus weight of the car. That takes care of all of the Y components, and it's the upward ones minus the downward ones. It has to be equal to 0. And then I can just say, what are these things? Well, if this angle lives here, it also lives here. So the Y component would be adjacent to that angle. So the Y component of normal force is n times the cosine of my theta. The Y component of my frictional force, well, that's opposite the angle that lives here. So that would be the sine function. So static friction times the sine of theta minus weight is just mg. I can then expand one more time to take no change to what I did to get the Y component of normal force, but then I can define what? Okay, I can say I'm solving for the maximum possible static friction here. So where I had static friction, I just replaced that I'm looking for the maximum possible. Nothing else changed. Why did I do that? Because at this limit of the maximum possible, I can relate this to normal force. They're related through a coefficient of friction. So now I get n times cosine of theta unchanged, but where I have maximum possible static friction times sine theta, I replace it with coefficient of static friction times normal force, because those two things are equal, times sine of theta minus mg. And then what I can do is I can try to solve for n. So pull mg across. group these two that have n in them. I'd have n times cosine theta from this minus mu s times sine theta from that. And that would be equal to mg, which I pulled across. And so then if I took that mg divided by all the stuff inside the square parentheses, I would then have a solution for n in terms of the mass of the car, the gravitational acceleration, cosine of the angle I have minus the coefficient of friction I have times the sine of the angle I have. So the only thing I don't have here is the mass. So I can't give you a number for the n, but conceptually I can tell you this is what it's equal to. All right, now we go to the x component. I did this in reverse order because I knew I'd have to work it this way. X component is where the thing I'm looking for is going to live, right? Um, well, ultimately, it doesn't live in either component, but the acceleration will live in the x component. What I'm looking for is actually coefficient of static friction, right? So I lied here. I don't know the coefficient of static friction. I would like to know it. No, I do know I'm sorry. I'm all over the place. I do know the coefficient of static friction. Um, so what I'm looking for is the speed. There it is. And the x component is where that's going to live because the speed lives in the centripetal acceleration because centripetal acceleration can be described as circular speed squared over r. So yes, F net x is ultimately where the thing I want is going to live. It lives over here. F net x equals max. In this case, that's m times my circular speed squared over r. So the rest of this middle part is just what is F net x? Well, I have two forces with x components. The normal force has an x component. It lives here. And the static friction force has an x component. It lives there. The x component of the normal force, well, if my angle's here, it's also here. That's opposite. The x component is opposite the angle, so that would be n times sine of theta. And again, angle lives here. X component for static friction is adjacent. So that would be static friction force times cosine theta. Okay, keep n sine theta. Reference the fact that we're solving for a threshold condition of the biggest possible static friction. If the car is to be going as fast as it possibly can, that is the limit, right? If we go any faster, it will slip. So we're going the fastest it can go without slipping. That means we would have our maximum possible static friction. So replace that. Then take advantage of the fact that maximum possible static friction can be described in terms of normal force and coefficient of friction, just like we did above. And we ultimately end up with this thing over here, which says n times the sine of theta plus mu s times n times the cosine of theta is equal to mv squared over r. Well, up here, we've described what n is in terms of mg cosine theta, rather theta and mu s. So I can take my definition of n from the y component and place it in where n goes in both of these terms down here. First, for simplification, I can group those to just have the n show up once. So mv squared over r from the right would be equal to, well, if I take the n's out of both of these, I'd have n times sine of theta plus mu s times cosine of theta. I can take what n is equal to, sub it in where n goes, and I would end up with, looks like I did multiple steps here. If I simply jump right ahead to solving for v here, I would end up with v max is equal to, well, this m is going to end up in the denominator over here, and this r is going to end up in the numerator over here. So I'd have n times r times this stuff over m, right? Let's see if that's how it plays out. V max is equal to square root, got rid of the square, r times n, that checks out, sine theta plus mu s cosine theta over m. That is then equal to, all right, so this was simply over here, V max is just rearrangement of this equation such that the m went in the denominator, the r went up in the numerator, the rest of this is just up in the numerator, square root to get rid of the squared on the v. And at this point, I can substitute in, as I was mentioning before, n in terms of what it's equal to, which is mg over cosine theta minus mu s sine theta. So mg would end up in the numerator where the n was, so that's where the n was times r. And in the denominator, I would get cosine theta minus mu s sine theta times the m that was already there. So this is now substituting what n is equal to into what this was. So we just substituted for this n. And what we see is we now have m times a bunch of stuff in both the numerator and denominator. So as will be needed, because we see we don't have the mass of the car, we can cancel the mass of the car. And we end up with GR, G is the thing I know, R is the thing I know, times sine theta, theta is the thing I know, plus mu s, thing I know, times cosine theta, theta is the thing I know, over cosine of theta, thing I know, minus mu s, thing I know, times sine theta, theta, thing I know. So now I have the thing I want in terms of things I know. That's always where I want to get to. I can solve for thing I want by just putting in what I know. So square root G is 9.8 meters per second squared. R is 100 meters. Angle is 25. Coefficient of static friction was 0.85. Angle is 25. Angle is 25. Coefficient of static friction 0.85. Angle 25. Do that math and I get 46.2 meters per second. Two significant figures, which I see in my mu s term at least, is 46. If you kept the 0.2, you would still get it correct. Question 4. Cart travels around vertical loop-the-loop at a steady 30 meters per second. How does your apparent weight, so we had to remember that apparent weight and weight are different things, otherwise we wouldn't need the adjective in front of the noun, right? You already have weight, so why describe it with an extra word? It must be something different. Apparent weight is the contact force responsible for supporting your weight. How does that compare to your actual weight? When you're at the top of the loop here, and the loop has a 75-meter radius. So we know the circular speed, we know the radius of the circle. That means we know the circular acceleration. We know the circular acceleration, or rather the centripetal acceleration. We therefore can relate that to the centripetal force. Centripetal force points to the center of the circle. When we are at the top of the circle, that direction would be down. So we know we would have to have an F net Y if we make the vertical axis with a Y component. And then we just draw a free body diagram. We draw a circle around us in the cart. What do we touch? We touch the track. Based on that contact, what could we have? Well, we could have a frictional force, but that would be horizontal, and that's not in the direction of our acceleration. And if we're traveling at constant speed, gonna have to assume that's somehow zero, or we have some pushing force to balance it. Either way, there's no net force in the x component. But we do have two y component forces where the track is horizontal at the top at that point. Normal force would therefore point down. We're below the track, so perpendicular to the plane would be downward. Weight force points downward. What does that mean? That means F net y in the down direction would just be equal to weight plus normal force. F net y is equal to weight plus normal force. That's equal to mg. That's our mass times gravitational acceleration, which is the definition of weight, plus normal force. And that's going to have to be equal to mv squared over r. That's just a definition of ma when you travel at a constant speed in a circle. Okay. Well, I can solve for n. Why would I want to solve for n? Well, because weight isn't my apparent weight. My apparent weight comes from the contact force supporting my weight. Well, there's only one of those. It's the normal force. So normal force is what I want to solve for if I want to solve for my apparent weight. Pull the mg across, and I would get mv squared minus r minus mg. If I group the m's, that would look like m times v squared over r minus g. I know v, I know r, I know g. So I can solve for this in terms of m, and I would find that my normal force would be equal to 2.2 meters per second squared times m. Well, what's my weight equal to? My weight's equal to 9.8 meters per second squared times m. Who's bigger than who? My weight would be bigger than my parent weight. That's something conceptually to remember. So my number should be less than 1 for my answer here. And if I solve this thing through, 2.2 divided by 9.8 is 0.224. Take the weight, multiply it by both sides, and I would be able to say that my apparent weight is equal to 0.224 times my weight. Two significant figures again looks right. That'd be 0.22 times my weight is my apparent weight. All right, finally, question 5. Geosynchronous satellites remain permanently fixed directly above specific locations on Earth's surface. We're told the mass of Earth. And then we're asked, what's the speed of the satellite? What speed must the satellite be traveling at to maintain this circular trajectory? All right, doesn't seem like we're given a lot. There must be implied information. First thing you have to realize is that if you are on the surface of Earth, you are moving. You're moving about an axis of rotation. How long does it take to complete one cycle around that rotational motion, one revolution? It takes 1 day. 1 day is 24 hours. 24 hours is 86,400 seconds. So the period for one rotation of this satellite, if it's going to remain fixed directly above someplace on the surface of Earth, must match that. So the orbit must have a period of 86,400 seconds. That's implied information that you weren't given directly. You were given implicitly by the fact that geosynchronous satellites remain fixed above a specific location on the surface of Earth. You then have to know that the surface of Earth is rotating about an axis of rotation, and this is the period of that rotation. Cool. Why do we care? We're looking for a speed. We care because if we would have gone directly to solving for the speed of an object in an orbital trajectory, we would see that we have an equation that does that. It depends on big G constant, which we have. I think I failed to put that at the top of this quiz, but you could have looked it up in your notes, etc. The mass of the thing that's being orbited, we have that, but then you have to also know the radius of the orbit, and we don't know that. But we do have an equation that relates the radius of the orbit, the mass of something being orbited, and the period of an orbit. So the reason we want to make use of the period is it allows us to get the orbital radius. And if we have the orbital radius, we can use that to get the orbital velocity we want. So once we get the period, here's our equation for what a period is equal to. Period relates to orbital radius and mass. We have mass, we don't have radius. We can rearrange this to solve for the radius, in which case we're going to end up with a cubed root of all this stuff. T squared, that just ends up going, let's see. So basically to get to here, what did I do? I squared both sides. I pulled the G across to the numerator, the mass across to the numerator. So T squared GM, that's how I got that. Divided by 4 pi squared. Okay, that goes down there. That would then leave me R cubed. And if I want just R, I have to take the cubed root of both sides, hence the cubed root of all that stuff. Put in what I know, 86,400 seconds where period goes, G, that 6 something times 10 to the negative 11 Newton meters, what would it be? Meters squared per kilogram squared. Mass of the planet, thing I know. 4 pi squared is a constant. I would get 4.3 times 10 to the 7 meters. That must be the radial distance center to center where geosynchronous orbit happens. Well, once I have the radial distance, the orbital radius, I can use that to solve for the orbital speed. Since I already have the mass, put that in, and I'll find that you must be traveling at 3,000 meters per second.